Buddy, welcome to the Jasmine Ballroom. We have brute forcing lockdown hard drive pin codes here with Colin O'Flynn. I have a few things to say before we actually get started here. To start off at the business hall located at Bayside AB during the rest of the day for the welcome reception, basically from now until 1900. The Black Hat Arsenal is going on at the Palm Foyer on level 3. And join us tonight for the Pony Awards in Mandalay Bay, BCD at 1830. Everybody, if you could make sure your cell phones are silent, appreciate it. Colin?
All right, thank you very much. Thanks for sticking around to the end here for my presentation on attacking these lockdown hard drives. So I hope you learn a little bit about how the drives work. And this presentation was really supposed to be about, reverse engineering them, how do you validate the security of them, and along the way, a sort of quick little mini hack. I'm behind a project called Chip Whisperer, which if you haven't seen before, it'll be at Arsenal tomorrow at some point, like 4 p.m. or something like that. But you can come check it out. It's sort of an open source tool for doing all sorts of side channel power analysis and glitching. So these are sort of more advanced types of hardware hacking attacks where we're really looking at what a device is doing on a lower layer. All right, so what's this presentation about? This presentation is about a certain type of AES 256 encrypted, as all the marketing and material was keen to point out, hard drive. In particular, the specific one I'm looking at is this guy right here. So this is a Lockdown brand, or Lockdown was the name of this particular drive. It didn't have any sort of FIPS rating or anything like that. So there's a few different versions of very similar looking drives you'll see, but they differ drastically internally. So for example, there are some that have some FIPS 197 ratings. So there's a few manufacturers of this. I'm not looking at this type of hard drive. I'm specifically looking at these sort of slightly lower end ones. But unless you really look into it, you may not even notice the full difference between them. And the specific drive I'm looking at, there's quite a few that use a similar internal structure, and that's what we'll dig into a bit when we say, we don't want to break just one specific manufacturer's drive, we want to look at a whole bunch of different ones. And so this also came about when I picked up the drive. I found there was some other work that people had done on a different drive, but it used the same internal chipset. So this is when you start finding out, oh, hey, this chip is used in a whole bunch of places. So Zarni and Rigo presented last year at hardware.io this really great paper that dealt with, how is the firmware loaded? How does the drive itself work? So basically what happens is that they found out that when you have these enclosures, you put a drive in, you hit the special format it button, and that's writing some data to the drive that helps decide how to encrypt the drive and stores the information about the keys. So they did a ton of work on that. I'm extending it a little bit and also presenting a new attack. All right, so the first part is just the brute forcing. This is like the easiest attack, and it only works against this specific drive, but it gives you an idea of what's the easiest hardware hacking type attack we can do. So in this case, what I did is I ripped apart the drive, and unfortunately, I don't have a good photo of it not destroyed like this, and we'll get into why in a moment here. And basically what you can see is the hard drive is on the bottom here, and it's plugged into the main board is the little green board on the left there. And so that's the USB to SATA board that was inside the enclosure. What I've done is there's a little flash chip over here that I've desoldered from the board and sort of made into a daughter board that can plug in. So this lets me modify it a lot easier than if it was on the board. There's an LCD to the top part here, and so this LCD is where it displays status information, asks for the pin code, stuff like that. And finally, there's a little header underneath the LCD that you can't really see, and where this header plugs into is the front panel board here. So this front panel board, if you go back to this photo, is where it has all these buttons that you're pressing and stuff like that. So that's sort of the user interface for entering your pin code. And on this front panel board, there's just a little I2C capacitive touch sensor. So what this means is it's just detecting where you're pressing, what buttons you're hitting, and reporting it back to that main board. And this is done over a little tiny header here. And I didn't have a cable that fit that, so you can see I soldered this huge cable onto it. And this basically means, you can have the drive open, you can tap it and see what it's all doing. So if we sort of break it apart, this is what it looks like. There's that main chip, that MB86311A. Inside this, it's an ARM Cortex-M3, so it's a little 32-bit microcontroller. Nothing too fancy, but it's a fairly well-known microcontroller core. Inside it, there's an AES peripheral, so this is where it does the encryption and decryption of your drive. And basically, if things are working normally, you have your hard drive here, it gets connected through this AES peripheral out to the USB. So the only thing that the drive needs to work is what the encryption key should be for that AES peripheral. And to get that, it has this I2C bus, so it's going to ask you for a PIN code on that front panel. If the PIN code matches what it expects, it loads the AES key into that peripheral. It also has an LCD bus on that's hanging off, or an LCD that's hanging off the I2C bus, and so everything's communicating over this one bus. Finally, down here, this little SPI flash, that's that chip that I had pulled off and had on a separate board. So this chip stores the firmware that's running. So this is the code running inside that Cortex-M3 device here. And it's basically telling the chip, hey, how do you actually generate the AES key? So this is really critical because if we knew exactly how it was generating the key from the PIN code, we could do a lot faster attacks on this board. But the first attack I thought of trying was just basically emulating this keypad here. So we have a keypad. We could say, well, why don't we manually see how quickly we can put in PIN codes? And there's a delay. It's not a completely terrible product. And so if you put the wrong PIN code in 3 times, it locks out for either 30 seconds or a minute or something like that. But what we can do is you can find a datasheet for the chip or a similar version of the chip. And you can see there's this reset pin here. And so we're going to try using that reset pin and just to bypass the delay. I was looking at the device operating, it seemed like it never wrote the current value of the delay to the non-volatile memory. So what this means is that I can get a little development board. I'm using an Atmel dev board. You could use an Arduino. You could use anything else that lets you do sort of basic I2C communication. And what I'm going to do is I'm going to wait for the device to poll the front panel. So it's going to say, has any buttons been pressed? I'm going to feed in my guess, and I'm going to see if that worked. And you can see there's some code that I've pushed to GitHub that does this on the Atmel dev board. And it has sort of comments on what pins you would hook up if you want to try that. And this is what you end up with is once you release the reset, it initializes the LCD, which happens after about 0.2, 0.3 seconds. There's a bit of a delay, basically, where it's spinning up the drive. It has to read some data from the drive. After that's done, it then starts polling for button presses. So unfortunately, it's not super fast after reset to come out, so this will limit how quickly we can actually do this particular brute force attack. But it does mean that because the timeout's not stored in non-volatile memory, it's pretty easy to bypass. There's a reasonable entry speed and force, but within half a second you can put in 4 or 5 digits at least. So it's pretty quick for the brute force attack. The main issue is this boot involves about 1.5 seconds of delay. It's also possible to reduce this, so if you mirror the drive to an SSD or things like this, you can improve the speed. But even on sort of the worst case scenario, what you end up with is, if they're only using a 4-digit pin, the drive accepts between 4 to 8 digits. You can brute force it pretty quickly, 6 hours. Again, this boot delay is killing you. 5 digits you get into days. Beyond that, it's pretty unreasonable. So that was sort of the initial attack on the brute forcing of the drive. But it does show if someone just picked up your drive off the ground, it would be pretty easy for them to figure out the pin if it was only a 4 or 5 digit pin. Now, I mentioned that I don't have any not ripped apart drives, and that's because when I went to order one in July in Amazon Canada, which doesn't have as much as your amazing Amazon here, they said, we got it in stock, don't worry. I ordered a bunch, and they just canceled the order. And since then, I haven't been able to find it basically anywhere. So I think it may have been discontinued, which sort of made the brute force attack interesting, but not really relevant to this or to future. So the more interesting part is looking at, okay, let's look at the actual chip and see how secure is that. Because if we can figure out errors in this particular chipset, it's not just this one drive, it's any using this type of chip. So the previous work, as I mentioned, Zerny and Rigo, they said that the security is basically a failure, and they were using a different manufacturer's enclosure. What they did is they took a drive that had been encrypted in one drive, in one enclosure, and moved it to another enclosure. And that second enclosure decrypted it fine. So this means all the secure information is stored on the hard drive. This means that if you can figure out what's in the chip, you should be able to just decrypt any hard drive you're given without having any issues at all. And now the only thing that they could have done to prevent that this test wouldn't actually prove, is that there could be fuse bits inside the device, and they could be manufacturer specific. So every drive enclosure programs some special key into the chip, and it won't work if you moved it to different manufacturers. You'd have to guess those or figure out what those key bits were. So this would be a reasonable step, but it's not done. So I bought a gray market chip off AliExpress, swapped it in, and the drive worked fine. So there's nothing manufacturer enclosure specific inside that chip. Any of them are using the same hardware. So the next thing is to understand the firmware file itself. So again, from Zerny and Rigo, they figured out that there's basically a stream cipher. What I'm showing here is this is two files that are a different version of the firmware. And in red is bytes that differ. In white is bytes that are the same. So you can see there's only a handful of differences. The first sort of 32 bytes are all different. And then it's very constant. Later on in the file, you get more differences. But this is like the boot code and stuff that would be, as expected, constant between versions. So because this is a stream cipher, basically it means we have a key stream that's either generated from some cipher in a predictable manner or a one-time pad, something like that. And it's XORed with the original firmware file. And this results in our ciphertext. What this means is you can even compare between different manufacturers. So these are two different manufacturers of enclosures using the same chipset, different board designs, everything. It's not just the same boards in it. And again, we see a lot of similarities. The initialization code at the beginning here must be all the same. So they're probably using some SDK that's showing them how to build this. The only other sort of question is, what is this file? We'd like to be able to modify it a bit to start hacking on this device. So one thing you can see when you sort of look at the file, the first about 4 bytes or 1 word, this is a 32-bit device, appears to be like a length. There's a hex length that matches almost exactly how much data there is. There's a few bytes that are sort of all zeros, and then with 1 or 2 bit set, that seems to be a flag byte. And there's still those 32 bytes at the beginning that we'll get to. What we also see, so this is a standard Cortex M3 core. On the left is just a code I've built for another M3 core. And one of the things is right at the beginning of the file, we have a bunch of these interrupt vectors. On this M3 device, there's 4 words that are reserved and will always be 0. So if you look in any M3 firmware file, you'll see a bunch of zeros. So you probably can't see the zeros, but that's this little block here of words that's all zeros. Now, if you look in the firmware file, the encrypted firmware file, what you end up seeing is that there's a block down here. You can see me sort of highlighting it. It's not zeros, but it's constant. Every version of the firmware you look at between different manufacturers, those 4 words are always the same. We then see some words that vary, and then another block of words that are the same. Or sort of two words that vary, and then another block that's the same. And this is what we'd expect because we have 4 here. Those are 0. We have 2 that vary, and then 1 more that's 0 that vary. So this basically tells us right away this is direct ARM Cortex M3 code, and it's just encrypted with a stream cipher. So there's nothing else involved in this. If we break the stream cipher, we will then be able to reverse engineer what the actual process is to generate the encryption keys on the drive. So to do this, or to sort of start to do this, this part's ongoing. So the previous part was a really simple type of brute force attack, and now we're looking at how could we make a better brute force attack. And really the answer is just how can we sort of validate the security of it. So I'm using something called power analysis. And what this is, I've done a bunch of other presentations on this, but very briefly, as you set bits on the data bus, it has some relation to the power consumed by the device. So if more bits are set on the data bus, you end up seeing a larger spike in power at a very small instant in time compared to no bits are set, so they're all 0 on the data bus. And this works very well, so you may not believe me, but this works extremely well for breaking encryption, for determining what a device is up to, and all sorts of things. So to do this, I have that chip, and I'm basically going to do power analysis with a little resistor here. I feed the data into my hardware for doing measurement. At the same time, so this is the flash by flash memory that we talked about earlier. So this is all the firmware for the device. It's going to load that firmware into the device. I can watch what it's doing while I change what sort of firmware is loaded. To do this, basically I take the chip. This is the bottom side of it, and there's a bunch of little wires soldered onto it. So this was before I made a dev board. So sort of a late night project. And that chip is down here somewhere, so you can't really see it in this photo, but that was, this little dead bug style chip there. We're triggering on some pattern that we're going to look for with the scope at the top. We do the power analysis here, so that was the Chip Whisperer project, and there's a bus pirate that can reprogram the flash memory. So what do we start to see? Beginning, I have the file. I've modified it a tiny bit to make it an invalid file. Looking at the datasheet for the MB86C311A, that chip, it says, oh, by the way, we use verification of the firmware. We have a signature on it, and it's encrypted. So I knew there should have been some sort of verification. And the problem was I had to know, is it decrypting it first and then checking the signature, or is it checking the signature first and then decrypting it? So to help answer that, I used power analysis to really directly see what it's up to. So this is what the power trace on the top in green looks like. So this guy here is the power trace. And the bottom is the SPI traffic. And so basically there's a big chunk here where it's loading the data. So that's not really of interest. There's that delay at A where it's doing something. And then it writes some stuff to the SPI flash and sort of keeps going. Now, in the other case, where I have a valid firmware that works fully, we see something very different. So you see right away we go from having that little function A, it does something new at B, and also at C. But this big jump at C, we don't know exactly what it is, but this we could make a guess is the verification of the signature, or the decryption, sorry. Because it's always going to verify the signature. Only if the signature correct is it going to do the decryption. So we assume this is decryption. So they both complete A. Only the valid code completes B. And probably C is, switching to the regular operating code, maybe powering on SATA or something like that. So what is that operation exactly is the question now. One way we can confirm this is I've written FFs at that location in the firmware file where I know it should be don't cares, or it should be reserved, so it shouldn't really matter. I can then look at the power as the device is doing this operation. And this is like so the raw power, you see that same sort of thing. There's a bunch of spikes here. That's not very interesting. What's more interesting is a differential trace. So this is the device, the difference in the power consumption when it's operating with FFs in some position. So the blue trace is when the first word is all FFs. The red trace is when the second word is all FFs. And you see a few things right away. You see A, there's like a tiny sort of delta between the first two peaks. So this is suggesting, there's a big for loop that's doing this, whatever this operation is. The second thing we see is that there's, multiple locations where it seems to be dealing with this data. So it's not just dealing with it once, which would suggest perhaps decryption, but instead it's dealing it with multiple times. So it's some sort of operation with, like a feedback, because maybe it has some delay elements that's sending the data through, XORing it with something and sending it back here, something like that. And so this right away suggests that it's a hash operation. And so now the question is, what is that hash? And I basically made a small Python script that just imported from hashlib what algorithms it knew of. That way I didn't need to know about them. And just tried various sort of variations of it. And at the bottom part, there's this starts with, so that was the known, these first 32 bytes, I guess, if I go back here, these first 32 bytes, I guess, were probably a hash. So this was for one firmware file. I just said, well, let's look if hashing various areas of the file generates this. And that actually worked. So then I was able to figure out, okay, we can now generate a hash with SHA-256 of the firmware file, and it'll accept it, and now it'll decrypt the file. So the ongoing work is actually breaking that decryption. Right away, we can cause it to load arbitrary code. It's not necessarily decryptable yet, or it's not something that we can definitely cause it to load, a specific operation like let's load a memory dumper. But with this, we can now start to investigate that decryption code because it can now decrypt arbitrary code, not just valid code. And so doing the same sort of power analysis, what I've done, and the red and blue traces are the differential traces. In blue, we again have the case where the first 512 bytes are all FFs minus where they're all zeros. So anywhere it's dealing with, byte 0 through 511, there's a sort of a larger blue spike. So we see a larger blue spike. In cyan near the bottom is the actual power trace. And you sort of see it does some sort of load on the input data. There's a big spike. And then there's another little operation, which I assume is unloading or writing it somewhere else in memory. And then it deals with the next block, so the next 512 bytes. So right away, we can get an idea of where it's decrypting it, but we still need to figure out the exact algorithm at this point. It may be that they're using, the AES hardware crypto in the device as some sort of stream cipher, which wouldn't be unreasonable and would explain this large peak here. But it is useful enough that we can cause arbitrary code to be decrypted. You could try moving around the reset vectors quasi-blindly. So that is, you can flip bits at least, because we can now cause any sort of modified code to be signed and loaded okay. And if we could determine even just a part of the stream cipher, or part of that code, so if we could figure out, for example, what init routines are being used there, they're probably fairly standard. You could build a short dumper program. So if you could fit a program that simply reads out memory and dumps it in that first little constant section, you may be able to get access to the code that way. But fundamentally, the problem is that there's no secrets stored inside that MB86311 device. So they didn't have any sort of manufacturer-specific fuse, or if they did, it seems like most people weren't using it. And again, that's because I was able to swap the devices. Almost all the devices seem to use that same firmware key stream, seems to be the same. And it's even used there's a version without AES that's used in the PlayStation 4. And it has the same you see the same pattern in the firmware. So it means any company using these devices could decrypt the firmware from another company. And once that's known, basically everything is lost. So if you're asking, how secure are these hard drives? Number one, you definitely can brute force them in a reasonable amount of time for 4 or 5 digits. But more critically, there could be someone out there who's able to read this firmware. And there's many companies that make these drives, many companies that would have access, presumably, to this stream cipher. And then once you have that, it's sort of all lost. And we also have flaws in the the firmware itself, due to the fact it just uses that SHA-256, I think, it would have been preferable such that there's some sort of signing operation that required me to guess a secret key. That's what I really would like to see. But I'm able to sign sort of any firmware I load on the device. So that's sort of a summary of the brute forcing of the basic pin code, and then how I'm starting to analyze the actual security of the firmware itself. So I know it's a kind of quick presentation, but thanks for sticking around. And if you have questions on any aspects, I'd be happy to take them.